Okay, so we have a decent amount to cover in this, the second half of today's class. I think a lot of it is familiar to you guys, so I'm gonna kind of move at a reasonable clip or pace. But if anything goes too fast, don't hesitate to raise your hand and just say, "Wait, can you hang on before you move on?" Or whatever we have. Okay. All right, so we're going to just talk about, so this is now chapter 2, and this is descriptive statistics, okay? Okay, and the big idea behind descriptive statistics is that we are going to take a large amount of data, okay? So so this basically just provides numeric summaries of our data, okay? And so think of your data as kind of this big entity, perhaps a little bit little complicated or complex, okay? And we're just trying to summarize it with just, one or two numbers, okay? It's trying to basically, it's like when you go in for a job interview and they ask you, tell me a little bit about yourself. It's a hard thing to try to say, well, I'm a complete person. How can I summarize my being into just a couple sentences? And that's essentially what we're trying to do, okay? By summarizing it into just a few numbers, it's very useful to make comparisons from one data set to another data set, okay? But you're going to miss out on details, okay? So you can talk about a country and look at, we come up with these different numbers, right? The HDI, which is the Human Development Index. And we say oh, Norway has a score of 94 and the US has a score of 93 and some poor country has a score of 25 and this is an indicator that these countries are very developed and life is fairly good and easy for the citizens of that country, and in these other countries it's much more challenging or hard. But it doesn't tell you much more than that, okay? Or if you talk about sports, if you watch football, the quarterback gets a passer rating at the end of a game, okay? And you can therefore compare one quarterback's performance to another quarterback's performance just with a single number. It doesn't tell you, well, maybe this person had a poor passer rating or poor performance because the defense that day was really terrible, and or the offensive line was really terrible, and he got clobbered by the other team's defense. It doesn't tell you all of this stuff. It's just we're summarizing it with single numbers, okay? So it provides numeric summaries of our data. These are especially useful when making comparisons between data sets. Okay. And so we can think of storing our data in a data table, okay? And the way our data table is structured is that every row okay, so each row represents an observation. Okay, observation, or we might say this is an observational unit. Okay, and so you have one for every person. Okay, so if the sample has n people. Our data table has n rows. Okay, and so we will often say n is equal to our sample size. All right, each column is a variable. Okay, and so for example, we can go around and we can ask students, you know, what is your name, what is your age, and what is your gender? Okay, and you know, we could collect other bits of information. Okay, and then so maybe we have Joe, who is 27 and male, and we have Jenny, who is 25 and female. Okay, so that's what we have. Okay, and then we would have, you know, basically one row for every observation or observational unit. And so we have each column as variable. So variables are just basically bits of information that we collect, and we have two types of variable. We have categorical variables, okay, and these tell us what type or what kind okay, and we also have numeric variables. That tell us how much or how many. Okay, and so in our little example here, name could be considered a categorical variable. Some texts might say that this is not a categorical, but it's rather an identifier. So an identifier would be basically a variable that is unique to that row. Okay. Age would be numeric, telling us how many years this person has been alive. And gender would be categorical. Okay. Yeah, question?
Would a yes or no variable be a categorical or numeric?
Yes or no would be categorical. Okay. Things get a little weird when you turn things into zeros and ones. Okay. And I guess it depends. So there are certain categories in life that also correspond to a number. Okay, so for example, like gender, which you know, for most people is just this categorical thing. You know, male or female. We could turn it into a numeric and say, like, how many Y chromosomes do you have? And people would answer 0 or 1. Okay, you know, there are exceptions to that, but you know, 0 or 1, and that is basically an analog for the categories male and female, things like that. You know, we could look at vehicles and say what is its body style, and it could be a coupe or a sedan. Or we could say, how many doors does this thing have, and it will be 2 or 4 or something like that. Okay, I don't know. Okay, so sometimes, you know, basically what I've done is I've categorized our variables into categorical and numeric variables, and you know, as life always is, it may not always be as simple as that. Okay, and so but you know, overall, you know, we can say things are categorical or numeric. But not everything that is traditionally categorical or numeric is that way. So for example, age can be numeric, as it was in that table. So, you know, if recorded in years. So, you know, most people will answer the question if in a certain way. If I said, how old are you? Okay, if you're not taken aback by the kind of the rudeness of the question, you would just say, oh, I'm 27, or I'm 35, or whatever. Okay, you would respond with a number. This is most people. Okay. However, if you were Nielsen Research, okay, they come up with these TV ratings and stuff like that. They don't actually care about your exact age. They would say you are in the 18 to 24 demographic, or you're in the 25 to 49 demographic, or you're in the 50 to 60 something demographic. Okay, they categorize age, and based on the category that you fit in, they try to market certain TV shows or whatever products to you. Okay, so age can be numeric, age can be categorical. Okay, or, you know, in the eyes of the law, there's only two categories. You're either a juvenile or you're an adult. Okay, and so, you know, if you or I guess, yeah, whatever. Okay, so you know, you have 18 to 24, you know, 25 to 49, you know, 50 to 60, whatever, something like that, right? These are just different demographic age categories. Okay. You know, certain things that appear numeric are actually categorical. So for example, we've got zip codes and area codes. Okay, you know, if your area code is, you know, 310 versus, you know, 626, okay, it doesn't, you can't say I have 316 more area code than you, okay? That's not a useful statement to make. So this does not tell us how much or how many. It's just an arbitrary label, okay? Based on where you purchased your cell phone plan. Okay. All right. So to summarize this data, okay, so we can summarize categorical data with frequency tables. And so we could talk about the example here is the color of a flower. Okay, so we're looking at poinsettias, and we've got the color of the flower, and it can either be red, pink, or white. And we look at the frequency or the count. 108 versus 34 and 40. Okay. We can also create a column called relative frequency. So there's a total of 182. And so so the relative frequency, all we do is we're just turning these into percentages. So I would do 108 divided by 182, and I would get something like 50. 59%. And 34 over 182 gives me 19%. And 40 divided by 182 gives me 22%. Okay, so that we have that, a total of 100%. Okay, so basically, you know, if we think of the data table itself, the actual data table, how many rows does it have? Corresponding to the data that we, No, this is our summary table. This is a summary table. The actual data table that we have summarized has how many rows?
182.
Has 182 rows, okay? The actual data table has 182 rows, right? One for each observational unit, which would be each flower, okay? Okay, our summary table has really just 3 rows. Okay, one for each color. So when you look at the summary table, well, what kind of data have we summarized? What kind of variable? We've summarized categorical data, okay? So, you know, you look at this and you've got numbers, you've got counts that tell you how many, but the data that has been summarized is categorical data, okay? So. And we can display our data using a bar chart. Okay, so the bar chart is for categorical data. Okay, and the way the bar chart works is, let's see if I can do this. 20, so if I'm going to go, so I got to create a bar up at 59, a bar at 19, and a bar at 22. Okay, and so this would be red, pink, and white. Okay, so this would be percentage or relative frequency. So far, so good? Okay. We can also summarize numeric data in the same way with bar charts. But, well, actually not bar charts, they're called histograms when you do it for numeric data, okay? So the thing is, bar charts are for categorical data, and the arrangement of the bars is arbitrary, okay? Okay, if somebody wanted to put the order of the bars to be pink, white, red, that is completely allowed, okay? The order of the bars, it doesn't really matter. Now, we might have, you know, there might be a tendency to put bars in a certain order and things like that, but really, if you wanted to rearrange the bars in another way, there's no rule against it, because as far as the categories go, they don't really have an inherent order, okay? There is something called an ordinal variable where there's kind of an inherent order, like t-shirt sizes. There's kind of an inherent order of small, medium, large, things like that. And we're not going to talk about the special treatment that those variables get and things like that. For our purposes, we can just treat them as categorical variables. No problem. Okay. Okay, but we also have numeric variables. Okay, and so we can take. We can also summarize numeric variables with a frequency table, and the display is called a histogram. Okay. All right, so let's. Okay, so just imagine. You know what? I'm going to cheat, and I'm going to just copy a picture out of the textbook. Where did it go? Oh, maybe I don't have it. Okay, never mind. I can't do it. All right, so just imagine our data table. Okay, has I don't know, 40 rows. Okay, and we're going to create a frequency table for I don't know, one variable, age. Okay, and so what we will do is we will put the age over here, and we will have the frequency over here. And so maybe the age categories are 20 to 29, 30 to 39, 40 to 49, and 50 to 59. And let's say these are all the ages represented in our thing. So the data table itself, maybe the age values in the table could be something like 20, 24, 27, 32, 28, etc., 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 35. So you're getting actual numeric values, not these categories, but then you would go through and you'd count how many people. You'd say, oh, I've got 20, 24, 27, 28. I have 4 people in the 20 to 29 age range here, okay? And then so maybe you go through and you have 16 and 12, and somehow this has to add up. Does it add up to 40? I don't know, whatever. 4 plus 16 plus 12 plus 8, I think. Yeah, okay. So now we have a total of 40 people here, okay? So you go through and you do this, and so now when you create your display, we have the histogram, which we go through and now we create bars representing how the frequency, the height of each of these things. So I'm just kind of eyeballing this. Something like that, okay? All right, and with the histogram, you cannot rearrange the bars, right? Because they're associated with the number line here, okay? So this, we have age. You cannot rearrange the bars. And the vertical axis would be the frequency. Do we have any questions here?
So were you making a distinction between the histogram and the bar charts?
Yes. So the histogram is for numeric data, and you cannot rearrange the bars. With bar charts are for categorical data, and the arrangement of bars is arbitrary. Okay, and then stylistically, we generally don't put gaps between the bars and the histogram, and we generally leave gaps between the bars and the bar chart. But that's stylistic and doesn't really mean that much. Was there a question over there, do you think? Okay, yeah. Okay, and then also, just as tradition holds it, you kind of, the bar, you'll notice I've labeled these 20, 30, 40, 50, 60. You kind of generally select the kind of if they represent a range, you kind of just select the left value of the range and then assume everything, so I guess the range is really 20 to 29.999 or something like that, okay? And that's kind of how when somebody asks for your age, you generally say, I am 29 up until, like the week before your birthday, okay? And you might say, I'm 29, but I turn 30 next week or something like that. But, unless you're like 4, then, then you make a big deal about, how old you are, down to the half year or something, Okay, we also have dot plots. Okay, with dot plots, basically every row gets a dot. Row or observation gets a dot. Okay, and again, this is for numeric data. Okay, and so, let's say your data, if we just looked at, I don't know, the ages of children in a family, maybe they are ages 3, 6, 8, 10, and 15, okay? So this family had 5 kids, and we can plot this, right? We can start off at 0 and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, whatever, okay. And then so every child or every row gets a dot, and so you'd put dots. Something like this, okay? And so if you had 100 people in your data table, you would have 100 dots, okay? So in general, dot plots lose their value when you get really, really big data sets, okay? So dot plots are generally are not preferred. With the large data sets, okay?
It seems kind of a strange plot. So when are they ideally used?
So over with the histogram, you lose the individual detail, okay? So over here, you don't really get to see, like, are most of these people like early 30s or late 30s or whatever? You just know they're 30 to 49, 30 to 39 or something like that. You could get more definition by making your, we could have split our things to have like two columns per decade, okay? So then we would have a 20 to 24 and a 25 to 29 and a 30 to 34. And you can do that with the histogram and things like that. The dot plot will always show your individual values, and so in certain cases that might be nice. Okay. Let's see. I'm gonna skip ahead in the text, okay, to talk about the box plot. Okay, and so what the box plot does, and I'm gonna throw out some terms here that may not fully, which I will discuss later in today's lesson. So with the box plot, it looks like this, okay, and maybe something like this. You have a box, and the box is determined by 3 values. They are Q1, the median, and Q3, okay? Q1 is equal to the 25th percentile, okay, or equal to the first quartile, and that's why it's called Q1, okay? So you guys are familiar with the concept of percentiles? So 25th percentile means 25% of observations have values smaller than Q1, okay? So 25% of the observations have values smaller or less than, smaller than Q1, okay? And so Q3, what will that be equivalent to? The 75th percentile, okay? Meaning 75% of the data have values smaller than the third quartile. Okay, so if you have 20 values in your data set, Q1 is the spot where 4 values are, or wait, what did I say? 20? Oh, there's a spot where 5 values are smaller. Okay, if you have 100 data points, Q1 is the spot where 25 values are smaller. If you have 100 data points, Q3 is the spot where 75 values are smaller, okay? The median is the spot where half of your values are smaller, okay? So the median is also Q2, or the 50th percentile. Half are larger, half are smaller. Okay. These lines, this is also called the box and whisker. These are called whiskers. The whiskers extend to the largest point and smallest point that are not outliers. Okay. Or can I write this? Okay. Whiskers extend to the largest and smallest values that are not outliers. Okay? And as far as outliers go, these are these dots here. Okay? We set up imaginary fences, and if they fall outside of the fences, they are considered outliers. Okay? So I've got to go on to the next slide. I can't fit anything more on this screen here, so so just pretend like I'm continuing on this thing, if that's okay. Okay, so we set up fences at 2 locations. We have the lower fence and the upper fence. The lower fence is Q1 minus 1.5 times the IQR, and the upper fence is equal to Q3 plus 1.5 times the IQR. Okay? The IQR is just the difference between Q3 minus Q1. This is called the interquartile range. You can think of it as the width of the box. Okay, so when we had the box, so you're basically going to take the width of this box. This is the IQR, the width. Okay, and you're going to go 1.5 times this length. So this is 1 IQR, and then plus a half of that, and I'm just kind of eyeballing. So this is IQR, IQR, and then 0.5 of the IQR, right? So this is 1.5 times this IQR. This creates the upper fence. You do the same thing on the lower side. Okay, and then so down here you would have the lower fence. I don't know. Does my picture make sense? Okay, and so if you have any data points that are bigger or smaller than the upper fence or the lower fence, then they are considered outliers. Okay, so anything out here, these would then be, this zone would be outliers, and then anything over here would be outliers as well. Yes, question?
With the black box plot,
Uh-huh.
in this one right here,
Yeah.
is that basically, should those fences or the whiskers on the outside, should they extend out to where?
No, the whiskers stop at the largest point that in your data that's not considered an outlier.
I
Okay.
understand.
Okay, so the whisker ends at the largest point or the smallest point that is not an outlier. Okay, question?
Just more of a clarification.
Yeah.
So the whiskers extend based upon your data set,
Yes.
but the fences are based on your interquartile range.
Correct. Okay. Well, I mean, your IQR is also based on the data set. Okay. But where the, how do we decide, and this is just one method to decide what is an outlier and what isn't an outlier. Okay. There's like other, but this is kind of like a common and a good way to get outliers. Okay. And so we just say, find your 25th percentile, find your 75th percentile, okay? What's the difference between the 75th and 25th percentile? That's called your IQR. And then you multiply that by 1.5, you add that to Q3, and that gives you your upper fence. You take that value, 1.5 times the IQR, and you subtract that from Q1. That takes you down here. These set up these invisible line called the fences, and that's what distinguishes what is an outlier versus what is not an outlier. Okay, and then anything outside of that is an outlier. Anything inside is not considered an outlier, and your whiskers go up to the biggest point in your data that's not an outlier, or your smallest data point that's not an outlier. Yes.
The whiskers could theoretically go up all the way to the fence, and then anything after the fence.
Yeah, the whisker could go all the way up to the fence. The whisker, if your lower fence ends up like in, some territory that doesn't even make sense, then your whiskers won't even approach that, right? Okay. So, based on the values of your IQR, you could get a fence that's like in the negative zone for something that really only is positive, right? So if we created a box and whisker plot for the number of children a family has, I'm sure the lower fence is like -3 or something like that, okay? And obviously a family cannot have negative number of children, okay? And then so, when we look at these different things, we've got the box and whisker, we have the dot plot, and we have the histogram, and they all kind of have their own strengths and weaknesses. There was a very good one, and I hope I'm not wasting too much time here, but on Reddit NBA, there was a, let me see if I can find it. I can't, okay, no, I can't find it now. All right, now I'm going to waste time. But there was a very good diagram of dot plot and box and whisker plots that show kind of these superstars and how many points they score per game and stuff like that. And it was neat to see, especially if you're into that kind of stuff. Okay. Let's go back to histograms a little bit, okay? And we can say, I'm going to just create a histogram here. So keep in mind that this is numeric data here. Okay, and we can take this and we can kind of summarize the shape of this distribution with something that looks like this, okay? Do you agree? So this is our histogram, and I'm going to just kind of summarize it with a curve that looks like this, okay? And basically what this means is that whatever value we're looking at, this could something be like income, okay? Most of the people make about this much income, okay? This is most people. And then we have, a few extreme values. Okay, so, this chunk right here is probably something between like $40,000 and $100,000 a year or something like that. This is probably most, and then you have people below that and you have people above that, and then you've got people out here making like $1 million a year or something, right? And this isn't even to scale, because if it's out here, this is probably only like 500,000 or something. I don't know. Okay. So basically this just says so the shape we have here, oh gosh, what am I doing? And I'm going to just kind of make a more compact version of this. Okay, these shapes, these are what we call right-skewed distributions. Okay, and if you need help remembering this, just imagine stabbing some meat with the shape of this thing. Okay, so which side would you use as the skewer? You would use the right side. Okay, so this is right skewed, and this means you have a few extreme values way higher and none that are way lower. Okay, so if we said the average income is like, I don't know, $50,000, okay, in the United States. I'm just making that up, but it's something around there. Okay, let's say it's $50,000. If someone makes $1 million a year, and there are people who make $1 million a year, that person is making $950,000 over average. Okay, is there anyone making $950,000 less than average? No. Okay, the lowest amount of money that you can legally be paid as a wage would be like $0 or $1 if you're like on Steve Jobs when he was taking his salary or whatever. you cannot be paid negative money, okay? So there's a lower limit of 0, and so you're going to have what we call a right-skewed distribution, okay, where you have some that are much larger than average and none that are much lower, okay? So some values very high, none very low. Okay. So that's right skewed. You have this. What's this? Left skewed. Very good. Okay. And then you have symmetric. Okay. This would be like things like IQs, height, symmetric. Okay. All of these have been unimodal. Okay. These are both only one peak. So unimodal is anything with one peak, whether it's left skewed. This is unimodal, or I mean this one's right skewed. You have bimodal. Okay, 2 peaks. And then anything with more than 2, we generally say multimodal. Okay, can you guys think of anything that could be bimodal? Yeah.
Mortality rates by age.
Mortality rates by age.
Old people tend to die more often than middle-aged people, and infants, especially in other parts of the world, have a higher mortality rate than, 20-year-olds.
Oh, okay. Yeah. Wait, so let me think here. Okay, let me think about this, but I think the answer here, I actually have to say no, okay? You are looking at 2 variables. One is mortality rate, and then the other is age, okay? And so you're looking at a link between 2 variables. Here we're just talking about one numeric variable, okay? So I think what you would see a pattern, and that would appear later on in something like when we talk on correlation, when we're looking at 2 variables, okay? Here we're just looking at one variable, and when I say bimodal, so if we're looking at one numeric variable, okay, this is going to be like a cartoon version of of the phenomenon that we're going to experience. But let's say one numeric variable, we can look at testosterone levels in someone, okay? Testosterone levels in people. Okay? So everybody produces testosterone, okay? And that's for some medical condition you don't, okay? But in general, men produce much more testosterone than women, okay? And so if we were to if we were to look at our raw data table, and I have no idea what numbers should be, okay? But I'm going to just make up some numbers, and we're going to just pretend. So, we might see numbers like 8, 7, 9, and then maybe like 62, 65, 63, and then 6, 10, 71, 58, or something like this, okay? So this is, again, a cartoon version of what I'm talking about here. And so from looking at these numbers, if we look at this, and we had to guess the gender of this person or the sex of this person, we would say, oh, this person's probably female, this person is probably male, or something like that, okay? And when we create a histogram of it, we would see, this is a terrible picture, but this is what it would look something like this, okay? And so this zone right here, this value, this is the quote-unquote average male testosterone level. And this is the quote-unquote average female testosterone level. Okay, so here we're still just looking at one variable all by itself. But if we were to graph it in a histogram, we would see kind of two peaks, okay? And then so a person out here, this would be, you know, a male with high testosterone compared to other males. Okay, this person is most likely a female with comparatively low testosterone. Okay, and then someone here, we're not sure. It could be a female with high testosterone or a male with low testosterone. We don't know, okay? So, you know, maybe female with high level or male with low, okay? And well, and that could actually be the case with anybody, right? You could have, you know, you could have a female out here with just unusually high levels of testosterone, or you could have a male down here with unusually low. But overall, the pattern would be something like this, where, yeah.
Question.
Yes.
Could you explain to me how this isn't two variables? Because I think of the male versus female as one variable.
So notice in my data table, okay, I don't necessarily have to collect the variable sex. Okay?
And aren't those assumptions you're making?
Yes, I am making assumptions that could get me in trouble, okay? But, you know, so, you know, let's say, okay, you cannot hire people you cannot discriminate based on sex, okay? Now, let's say some weird company said, okay, well, part of your hiring process, we're going to have you spit in a cup and we're going to do some analysis, okay? And then the people, you know, they do the analysis, and then one of the hiring criteria is testosterone level, okay? They could effectively discriminate against women based on testosterone levels without necessarily having asked for the person's gender or something like that. It's just using this, it would be kind of a proxy for that. But we don't actually need to collect information about the sex to kind of make this distinction, okay? And so, you know, life gets complicated sometimes, and so, you know, trying to look at this and decide who's a man or a woman may not be a good idea. Well, ethically, it certainly is not a good idea to do that. And you know, there was actually a controversy with the Olympics. I don't know, now probably 8 years ago or something, because there was this girl, and she was totally amazing, and her opponents accused her of being a man disguised as a girl, and you know, and they said, oh, well, you know, she could have gotten surgery and all of this stuff, so you don't know, right? So it ended up coming down to checking testosterone levels and saying her testosterone levels are in the range of normal for, you know, normal woman, so she can compete as a woman. But that was kind of messed up thing to do, but, you know. Stuff happens. Castor Semenya, if you want to look up the thing. Okay. All right. So I got to talk about other numeric summaries. We've got the mean and the median. Okay. These are ways to summarize the, quote, central tendency of a data set, okay, of a sample of data. Okay. Sorry, I should have been using the black pen here. Okay, and I think we're familiar with these things. So the mean we calculate by add up the values and then divide by the sample size. Okay, and the median, you find this is the halfway point. You just find the spot where half are larger and half are smaller. So, a range from least to greatest. Find the spot. Half are larger and half are smaller, okay? If n is even, meaning you have an even number of data points, okay, then the median is halfway between the two middle points. And then if n is odd, then the median is the value of the central point. Yes?
Do you mean that if n is even, we'll take the mean of the two middle points?
Yeah. So, yeah, the median is the mean of the two middle points, I can say. Yeah. But it's also halfway between the two middle points. I don't know. Yeah, okay. So can also be, the mean of the two middle points. Yes?
Is the mode also a measure of central tendency?
Yeah, the mode is also a measure of central tendency. That is the value that shows up with the highest number of frequency. For whatever reason, our book does not include that in its definitions of measures of center. It is kind of, I guess, in a way mentioned when we talked about unimodal data sets and bimodal data sets, okay? Meaning these are values that show up more frequently, okay? Conceptually, you can think of the mean. The mean is the balance point of our data. Okay, so you could imagine a box plot, or not a box plot, a dot plot. Okay, and maybe our data set is 1, 1, 2, 4. Okay, so our data is 1, 1, 2, 4. Okay, well, the mean of these values would be 1, 1 plus 1 plus 2 plus 4, and then I would divide by 4, and so my mean is equal to 2, right? So mean is equal to 1 plus 1 plus 2 plus 4 divided by 4 data points, I get 2, okay? And what this says is that if we were to treat this picture as a kind of a plank with rocks or stones, and I wanted to make a seesaw, the spot where I would put the fulcrum or the little tipping point would be right at 2, okay? Where would the median of this data set be, of 1, 1, 2, 4 be?
1.5.
1.5. It's halfway between our middle 2 points of 1 and 2. So our median would actually be 1.5. Can we see that? Is 1.5. Halfway, half are larger and half are smaller. I should say half are smaller. Okay, so the mean is the balance point of our data, and then the median is our halfway point. Are we okay with this? Okay, and so when do we want to use the mean versus the median? Okay, so the mean is affected by extreme observations or extreme values. Okay, so if you have right skewed data, your mean will be, quote, pulled out in the direction of the skew. Okay, so the mean is affected by extreme values. The median is not affected by extreme values. Okay, and so if you have data that look like this, perhaps your I'm just eyeballing this, and I don't know if this is actually correct. So this might be the median, and this might be the mean. I'm not sure. Okay. Just eyeballing. Okay. So what the median says is basically if you shaded the area to the left of the median and you shaded the area to the right of the median, they would both have the same area. Okay, so the median would be area to the left and area to the right would have the same area, same value. Okay. Okay. Area to the left of median is equal to the area to the right of the median. Okay, and on the other hand, the mean, you'd have to think of this again as the little triangle fulcrum. That is the spot where our picture is balanced. Okay, the shape would be, the mean is the balance point. Okay, and so what this is supposed to show is that because it's right skewed, the median is right here and the mean is, quote, pulled out towards the direction of the skew. Okay, so the mean is, quote, pulled in the direction of the skew, which is really just the direction of the extreme values. Okay. And so which value should you use? Well, the question comes down to, do you want your values to be, do you want your summary value to be affected by these extreme values or not? In certain cases, it would be dishonest to leave out the effect of the extreme values, okay? Or maybe not dishonest, but just misleading. And in other cases, maybe the extreme values kind of distort what it is that you're trying to explain or something, okay? So for example, you could think of incomes at a company, all right? And maybe at this company the CEO makes, I don't know, 10 times more than the typical worker, okay? And so you might ask, what is the typical salary at the company? And in that case, probably the median salary is a good number to use, okay? But then if we're talking about, company expenses, okay, what is the average salary that we need to talk about when we're talking about expenditures? It might not be completely honest to leave out a huge expenditure, which would be the salary of the CEO or something like that, okay? So depending on your situation, you might prefer one over the other, or maybe you need to include both, but then people might complain that, why are you including both numbers or something, okay? So they serve different purposes there, okay? Okay, let's now talk about measures of spread, okay, or measures of dispersion. Okay. Hang in there, we're almost at the end of class here. Okay, so spread is the concept of, or dispersion is the concept of, are the values similar to each other, or are they quite different from each other, okay? So okay, so let's say there are two families. Okay, both families have 5 kids, and the average age is 9 years old. Okay, so for both families, the average age of the kids is 9 years old. Both families have 5 kids, okay? Let's say, family A, the kids' ages are 7, 8, 9, 10, 11, okay? And with family B, this sounds so, we'll call this family Adams and family Baker, okay, just because it sounds too, all right, let's say the kids' ages are 3, 6, 9, 12, and 15, okay? Both families have 5 kids. The average age is 9 in both families. Those are both true statements. But does life necessarily look the same in the Adams family or the Baker family? No, okay? So, all of these kids were, boom, 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 boom. There's, very, very close to each other in age range, okay? Over here, there's much more spread, okay? And so, this is a very simple example where we can clearly see that there's, more spread here. And over here we have less spread. And so we have numbers. We can kind of give numbers to the values of spread, okay? And so our to measure spread, we have the range, which is just equal to the max value minus the minimum value. Okay, so for the Adams family, the range would be equal to 11 minus 7. There's a range of 4 years. Okay, and for the Baker family, the range is 15 minus 3, a range of 12 years. Okay. Yeah, the relationship between the youngest and the oldest child in the Adams family will be a very different relationship from the youngest and oldest child in the Baker family, right? So this is so that's one way to capture the idea of spread, okay? But the range is going to be very, very, very much affected by extreme values. In fact, it's defined entirely by extreme values. So we also have the IQR, okay? The IQR, which we've already talked about, is the difference between the 75th percentile and the 25th percentile. So the IQR, or interquartile range, is another way to talk about spread, okay? This gets it's a little bit trickier here. It's not, you know, we don't have a nice number. We have 5 data points, so it's hard to say where 4 is, but I think we would say this is going to be Q1 and Q3, so and this would be Q1 and Q3. So our IQR here would be 10 minus 8 equal to 2. And over here our IQR would be 12 minus 6 equal to 6. Okay? And then the last measure of spread is the standard deviation. Okay, standard deviation, and that I will put on another page. Okay, and so these are just different ways to assign a numeric value to this concept of spread. Are the numbers quite similar to each other, or are they quite different from each other? Okay, and so the standard deviation, it might be easiest to think of this standard deviation is equal to the square root of the variation, or I'm sorry, the variance, okay? And the variance can be thought of as the quote-unquote average squared distance from the mean. Okay, and I put average in quotes because it's not exactly the average. So let's look at the Baker family. Okay, so the kids' ages were 3, 6, 9, 12, and 15, and the mean age is 9, right? Okay, so what we're going to do is I'm going to just create a few rows. We're going to have the distance from the mean. Okay, how far is 3 from the mean of 9? 6. Okay, how far is 6 from the mean of 9? 3. How far is 9 from the mean of 9? 12 and 15 are 3 and 6 units away. Okay, so this is the distance from the mean. You can also just think of it as, you know, we could technically just subtract off 9, and I could just do one way to get all of these values. I can just do minus 9, minus 9, minus 9, minus 9. But effectively, this would give us the distance from the mean, right? Okay, and all we have to do is we're going to square this distance from mean. Okay, so squared distance from the mean. So negative 6 squared, or 6 squared, is going to be 36. 3 squared is 9. 0, 9, and 36. So I'm squaring the distances from the mean. Okay? And if I said, what is the average squared distance? I would add these up and divide by 5, right? Okay, so the average squared distance would be add these up and divide by 5. But what we have here is there's a special rule, and it's called Bessel's correction. You don't have to worry about this. And Bessel might actually have 2 L's in it. I don't know. Okay. We're going to add them up. We're going to quote-unquote get the average, which is going to be add them up and divide by n minus 1. Okay, so I'm going to add these up and divide by 4 rather than 5. Okay, so I'm going to do 36 plus 9 plus 0 plus 9 plus 36. And we're going to divide by 4 rather than 9. Okay, so divide by 4 instead of 5. Okay, and so this value is the variance. It's the average, quote-unquote average, squared distance from the mean. So I do 36 plus 9. Okay, plus 9. Okay, so I get 90, and I do 90 divided by 4. And so this is 22.5. My variance is 22.5. Okay, and then so my standard deviation is just the square root of this. So the square root of 22.5 is 4.743. This is my standard deviation. Okay, and so this is just a numeric value that we assign to the this concept of spread. Okay, the formula for standard deviation, if you're into that kind of thing, is this, which is exactly what we did. Y bar represents the mean. Okay, and so all we did is we subtracted off the mean from each value y. We squared that difference, and we got all of these values. And then we added them up and divided by n minus 1. And then we took the square root. Okay, so this formula is basically just exactly what we've done here. But I think, I feel like this is a fairly good definition, the quote-unquote average square distance from the mean, whereas the average, you would add them up and divide by n. Here, we are adding them up and dividing by n minus 1, okay? And that's because of this funny thing called Bessel's correction, which is really beyond the scope of this course, but everyone always asks, why are we using n minus 1? And it's because it creates a it corrects the bias of the estimator, which, whatever, you don't have to worry about that. Okay, so we'll end here, and we'll see you guys next week. Okay.